So this lesson is called the sigma notation. And every time I read or say sigma, I like to say sigma because it feels good to say that. So, prior knowledge for this lesson. It's important to be familiar with function notation. That means f of x. The sigma symbol, which means to add up everything up to a certain point. We're going to get into all the detail about that today. And Gauss and Euclid's methods for sums are still going to be useful for some of the problems we're going to work on with this. And don't forget, Gauss is the one with arithmetic sequences, and Euclid's goes with geometric sequences. I don't have a warm-up for you today specifically, but I do want to introduce you to some notation that's new, and then we'll jump right off with an example. So, first of all, usually when we see sigma, I think for the most part for stuff you'll work on in your future classes, it still means sum, but we actually have some other stuff we write in with it. And this way that we write this notation is, again, just like a shorthand way to like put things together. Just like, for example, if I'm multiplying, a number by itself however many times, we can condense that and shorten it by using exponent notation. And same thing here. If I have the outputs of some function, okay, that are forming, and we list them in a sequence, if I'm adding them all up together, and there's many instances where it's helpful, think back to that inheritance problem, then we shorten that sum using this sigma symbol. And let's just talk about some of the specific things. You always have your starting input. Now, this is technically a variable, but it actually represents your physical number input that is going in throughout the sequence, right? So that's why this k is here, because it represents all the different inputs you're putting in based on wherever I'm starting and finishing. And we obviously we have a starting point and an ending point right now. And so down here I write k equals 0, which means I'm just starting at an input of 0. Now that doesn't have to be 0. We'll look at examples where it's not 0, but at this point we're just going to use that as a placeholder. I guess I could have put a or something. And then our final input, typically it's stated as m, especially sometimes we actually want to find a formula for that sum. We've already worked on that a little bit. N is generally my final, the variable I use as my final input. But for now, n actually represents the actual final literal number. So if I want to, for example, add up from an input of 0 to an input of 10 for a certain function, then I would just write k equals 0 to 10, and then you'd actually write the rule right here. Okay, so that's the actual function rule. Here's an important in words way of saying what's going on. This is the sum of the outputs of a function f of x with integer inputs, because the sum notation only works for what we call discrete situations, which are like countable, and in this case, integer based, right? Whole numbers or negatives or 0. Okay, from k equals 0 to n. And again, it doesn't have to start at 0. Okay, so let's jump in right away with an example, and we'll want to find the following sums. So here are our 3 examples. Okay, the sum from 0 to 3 of 2k, the sum from 4 to 7 of 2 times I minus 2, and you'll notice I'm using a different index here, and this I doesn't mean the same as like imaginary number I, it's just the index again. So k, I, j, whatever. Okay, we're going to do a together, and then after that I'll have you pause and try to tackle b and c on your own. Just as a recommendation for c, you'll notice that this is going to be quite a few things to add up, all the way from 5 through 19, but you might think about what kind of function this is and what kind of sequence it goes with, arithmetic, and utilize one of those methods. So let's look at a first. So it's helpful just to unpack this and write out the things, really. So if I'm saying 0 to 3 are my inputs, then this is the function 2x, like 2 times the input, right? So it's really just 2 times 0 plus 2 times 1 plus 2 times 2 plus 2 times 3. That make sense? And we can then just calculate this and get the final sum. And notice, we can actually think of the whole sum as its own function. And we've already talked about that. We'll dive into that deeper later. But a couple other things to think about here is, if we notice all these things added up, what is constantly happening in each one? The 0, 1, 2, 3, those increase, but then you'll notice that there's actually a factor of 2 in there for everything. So I'm just pointing that out. And we could, of course, just write this as 0 plus 2 plus 4 plus 6, and then this becomes 6 plus 6, which is 12, right? Okay. But you could have alternatively actually taken the 2 out and left 0 plus 1 plus 2 plus 3. And hopefully you recognize that itself as a nice arithmetic sequence, actually. But again, in this case, it's easy to just calculate it by hand. Okay, so this is kind of an OR thing. And then 1 plus 2 plus 3 is 6. So this becomes 2 times 6, which is 12, right? So I want you to think about patterns as you're working through the problems with this lesson, because they really, there's a lot that we can start thinking about and getting the gears going in our heads for how sums actually work and some rules, because as we move into our next topic here, as we investigate later, we're going to actually start talking about some of those rules. Anyway, so right now is the time where I'll have you pause and do B and C on your own, and then we'll come back and look at the solutions. Okay, so I'm assuming you've already worked through B and C, and let's check our answers. So, again, if we just list this out literally, I have to sneeze. I don't know if I should cut this out of the video. Maybe I'll leave it for you to laugh. Let's go ahead and do this. So you'll notice that I'm going from 4 to 7 here, so I start with an input of 4. So I get 2 times 4 minus 2 plus 2 times 5 minus 2 plus, I'm going to go into the next, save some space here, plus 2 times 6 minus 2 plus 2 times 7 minus 2. Okay? And that's going to give me 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5, if that makes sense. Is that okay? And then we're going to go ahead and do 4 plus 6 plus 8 plus 10, which is 10 plus 10 plus 8 is 28. So you should get 28 from that one. Okay. So you can go ahead and let me know if you have anything you're wondering about or you're unsure about with that one later, but I think you should be okay. And then let's look at part C. This one again, so this becomes 3 times 5, minus 4, right? Plus 3 times 6 minus 4. I guess I'm going to use parentheses, I don't know, just to make it obvious which term. And then I'm going to use my little dots because I don't want to write the whole thing out, right? And in the end, I'm going to need to end up with 3 times 19 minus 4, right? Now, I want you to think about this really carefully. You may have actually added these up all individually, or maybe you're like, nah, screw that, I'm not going to do that, I'm going to wait till Mr. Engel gives me the answer. If at any point you kind of get some clarity or a light bulb, you can pause again and finish it if you didn't already. But I want you to think about something really carefully. The only thing that's altering in this whole list is that number right there. 5, 6, 7, all the way up to 19. You'll notice there's a factor of 3 in every single one of them. And there's also just a minus 4 in every single one of them. It's not like a factor of minus 4, it's just, well, you can think of it that way, but it's just a minus 4. So these ones are a little trickier, but we can actually utilize, I already gave you a hint to some things we've done before, as well as maybe some distribution. I want you to see something. Do you agree? Do you see with me that there's actually a 3 times 5 plus 6 plus all the way up to 19? If I like rearrange all these, if I put all the 3 times whatevers together, and then all these negative 4s I lump together, and we just do plus negative 4 times, well, let's remind ourselves, how many terms are there? And earlier we kind of talked about one more than the difference, right? So 19 minus 5 is 14, but it's always one more than that if I start counting 5, 6, 7 all the way up to 19. So there's actually 15 things. So it's actually plus negative 4 times 15, or just minus 4 times 15. Okay, so I want to make sure you really convince yourself and you understand why this actually can be worked with in that way. Because then what we have here is this arithmetic sequence, and then just times 3, and then minus 4 times 15. So let's actually work on the side with that arithmetic sequence for a moment, and I'll come back, let's just work down here maybe, and then we'll come back to it afterwards, okay? Actually, let's leave that open. So 5 plus 6 plus all the way to 19. Remember, if we write it in reverse, 19 plus 18 plus 5 in the end, right? And then we do our 2s equals, and you may remember the trick at the end, like I'm just helping in case some of you don't remember everything. Well, 5 plus 19 and 6 plus 18, they all end up being 24, right? So it ends up being a bunch of 24s. And we already realized since there's 15 things, this actually is 24 times 15. So if we divide by 2, that becomes 12 times 15. And that's going to be 120 plus 12 times 5 is 60. So it's going to be 180. So I get 3 times 180 minus 4 times 15 is 60. And 3 times 180 is 540 minus 60, which is 480. So that one is a little bit of a doozy, I guess, a little bit more involved, but still entirely doable. Okay, so you see where we came back up with this. Again, if you kind of already knew the pattern, if you remember, we can take the first times the last, right? Does that make sense? Or sorry, the first plus the last. And that's where I got the 24. And then you just multiply by how many terms there are and divide by 2, right? Okay, we have a couple more examples and then we're going to be done with today's lesson. So let's look at those next. I actually decided to add one more on to number 1 here. We'll call it part D. And we'll just do it together. I mean, you can get some practice and do it on your own if you like. But let's look at this because it's actually going to be related to another one that we did real quick. So this one, we don't have to do what we did with that long way in part C because we're not really adding that many things up, but I want to mention something to you. It's 2 times, now k starts at 3, so 3 minus 3 plus 2 times 3 minus 4, excuse me, I switched them, 4 minus 3, my k is in front, plus 2 times 5 minus 3, and then finally 2 times 6 minus 3. And if you notice here, 3 minus 3 becomes 2 times 0, 2 times 1, and then 2 times 2, and then 2 times 3 for those terms. And this should look familiar because this becomes 0, 2, 4, 6. And we already actually did that because this gives me 12, and I think you should realize this actually is the same as part A. So I wanted to discuss with you a little bit right now of why these are the same. And it's actually a fairly simple reason, I guess, because you notice the function itself is technically not the same, right? 2, when you distribute it, becomes 2k minus 6, whereas that's just 2k, right? So they're not the same, and again, I like to leave it factored, but this really relates to translations and stuff like when we studied function transformations. And if you remember, if you have the variable minus 3, right, you have to counteract that by adding 3, right, by moving the opposite direction of 3. Whether we're talking, in this case, if this is inputs, the graph, if we're talking graphs, would move to the right by 3. So watch this. Because this is k minus 3 here, you'll notice they both are essentially involving 2 times some amount, right? Well, because that's a minus 3, if we start at 3, that counteracted the minus 3 and made it get back to 0. So, and each of these inputs starting at 3 have the same effect, and they turn them into what was 0, 1, 2, and 3 in this one. And that's what actually made me have the same sum. So you notice if I adjust by subtracting all the variables by the same amount, I can start my index at the number that counteracts that, and actually I have two things that give me the same sum. And this is going to be a good thought in our next example, because we're going to actually go backwards and we're going to start with a list of terms, a sum, and we're going to want to write it in this form. So we're not going to be given this. And the thing is, there's many ways to do it, but it's always okay just to start at 0, because that's usually the easiest, and that's kind of what we'll focus on. But this is important, and we'll be thinking more about those ideas later on, but I just wanted you guys to see an example of two that actually can give the exact same sum, and not even the exact final sum, but the exact same terms after you simplified here. Okay, so last example we're going to move on to next, and then we're done. Now, as promised, we're going to go in reverse. So the instructions are to condense the following sums into sigma notation. You notice I use the word condense just because this is like the expanded version, and sigma notation's purpose is to like make a pattern and condense it into something. Just like exponents were shorthand for like a condensed version of multiplying something repeatedly, and even multiplication itself can be viewed as adding something to itself repeatedly, and it's like a condensed way. So this is another one of those kind of symbols that does that, okay? But it's not just adding the same thing, it's adding something according to a certain pattern. So we have to identify the pattern itself first before we can do anything else, if that makes sense. So for these, they're a little trickier than the last ones, because we actually have to figure out, okay, well, what function is it that goes with the numbers that are given to me? And again, that harks back to our methods that we've learned in the past for finding closed form rules for things, right? Now, most of the ones you're going to have here are going to be, or I think pretty much all of them are going to be either arithmetic or geometric, right? So it'll either be a polynomial, in fact, not even a polynomial actually. I think pretty much all of them are going to be linear, or else they're going to be exponential related, okay? And we'll look at an example of each of those first, and we actually have more examples that go with number 2. But let's try to identify this here. Now, first of all, you know in the end I'm going to need this, and we can just go ahead and use k, and maybe it'll be helpful to start with 0, I don't know. But if we have 0, 1, 2, 3, 4, 5, there's 6 total things. So 0 to 5 gives me 6 total things. But the thing we're missing here is, what is the actual rule for this function that's going to make this work out? Now, if you notice here, this is going up by 4 each time, right? So it seems like we have 4k if that makes sense. The only problem is, if I directly did that and started when k equals 0, that's not really going to work out, because that should actually leave me with 3, right? And similarly, if I plug k equals 1 into here, that leaves me with 4, but I need 7. Okay. So again, you could list this out and make a table if you want, and think of these like inputs, or outputs, excuse me, 3, 7, 11, 15, 19, 23, if you wanted to, and just think of this as like 0, 1, 2, 3, 4, 5. And then from there, you're going to have to play with this, and there's lots of ways to go about this. It seems like if I do 4k plus 3, that's going to work. It also seems like, right, because if you notice, I'm starting at 0, and my starting output's 3, so that gives me the plus 3. And then since I'm adding by 4 each time, I have the 4k. So that's like a way to do this. If you think of this as like n and f of n, and then my difference table is constantly at 4, then we can get that answer. Let me write this in a better spot here. I thought I needed more space, but I don't think I do. K equals 0 to 5 of 4k plus 3. Seems like. That's not the only way to make it, but that's likely the easiest way to make that one. Okay? Let's look at the next one here. This one's weird because it says, okay, well, hopefully you can identify the pattern. This pattern's maybe a little easier to dig out than this pattern was. but 1 plus 3 plus 9 plus 27, etc. forever. Wait a minute, forever, Mr. Engel, what do you mean? We've always stopped somewhere. Well, just think carefully. What symbol do we generally use to represent forever, right? Meaning infinitely far. Well, we can just use the infinity symbol. That's actually pretty cool. So if we identify, we can use k again if we want, and we can start with 0. And if you notice we're doing forever, we can actually use that infinity symbol right here. That is actually a very common thing to do. And it seems like these are all just powers of 3 actually. 3 to the 0, 3 to the 1, 3 to the 2. So this would just be simply 3 to the k. All right? So there's 2 things. Let's look at a few more of them before we wrap up. Okay, these are our very last ones we're looking at for this lesson. Let's go ahead and start out. This is the point where I want you to pause and try to work through these yourselves, condensing and writing in sigma notation, and then we'll come back together. So go ahead and do that right now. All right, let's check our answers. You'll notice this is another arithmetic sequence, kind of like part A was, so we can check that guy out. Let's go ahead and start out. It's going to be, and we can do the same thing, k equals 0, in this case 0, 1, 2, 3. So 3, right? If there's 4 terms, just remember if you start at 0, it's up to 3 in this case, 1 less than how many there are. And if you want to list inputs and outputs like we did before to help you get work through that, that's also okay. But if you notice we're starting with 6 and we're adding 2 each time, we can just do 6 plus 2k or 2k plus 6, and boom, we're good to go. If that makes sense, right? Next one, you'll notice that this doesn't stop at a specific number, but it is, okay, so it's not a given number, but it is actually a set point. It's not adding to infinity like our other one was. But this kind of is a tricky one. Anytime this is here, it actually gives you the formula. So the trick is to figure out how many things we're adding. So if we think k equals, and it seems like this is where it gets a little bit tricky, because if this is 1, 4, 9, 16, etc., I think we can understand that it's n squared. If I wanted to use n squared there, I need to make sure that I start in the proper place. So if this was k equals 1, then I'd get my 1 squared, and then 2 squared makes 4, and then 3 squared makes 9, and then to n. So actually, even though that has n squared, I'm sorry, this should actually say k. That's my bad. This should always be with k. But we're going from 1 to n, so literally it's 1 using 1, then 2, then 3, then 4, all the way up to n, right? And that's exactly what this says. Now, there's an alternative you could have done. If you really wanted to start with k equals 0, what we would have to do is adjust this. Does that make sense? And the way to adjust this one would have to be making it k plus 1 squared. Okay, so I'm going to put a big or here. It could be k equals 1 to n of just k squared. But if I drop that 1 down to 0, I'm going to have to adjust this guy and make it k plus 1 squared. But both of these are okay and acceptable. Okay? Next one, basically the same deal, because we're actually given the way the formula, the formula in the end, which we could have probably picked out because, powers of 4. And this one actually, k equals 0, is a more natural start, because if it's 4 to the k, kind of like it's given to us, and that's again up to n, then 4 to the 0 is 1, which was my first thing, as opposed to this one, right? If I started with 0, then it'd be easy just to start this at 0 and leave it as it was. But this one starts at 1 actually, it doesn't start at 0. And then the last one, this one seems a little weird. 2 plus 2 plus 2 plus 2. It's just adding 2's together. Well, what function is it whose outputs are always 2? It's easier than it seems, maybe. Maybe you got it quick. But the function is just f of x equals 2, right? Or f of n equals 2. So actually, this is weird, but we don't need to use a variable there at all, because the variable is not determining what the number is, since it's just a constant. So k equals 0 to 3 of 2. And in fact, we could do 1 to 4 or 5 to 9. As long as this ends up making 4 things add up, actually, it doesn't really matter, and we don't even need to do any adjusting because that doesn't even have a variable in it in the first place. So that's kind of weird how it works out that way. But there's everything that we need to prep you for working on on using sigma notation. So happy math, see you next time.